Hello everyone. In this video, I'm going to discuss mean and RMS values of periodic waveform. If you are new to the topic of mean and RMS value of a function, I would recommend that you watch the previous two videos. Alright, so mean and RMS values of periodic waveform. So what is a periodic waveform? A periodic waveform is a function that exactly repeats itself after a period of time t. So if we want to calculate mean value or RMS value of a periodic waveform, it is sufficient to calculate them over just one complete period. Thus, the mean value is given by, so we done that before. So 1 over t is the period, and integral of f3 from 0 to t. Because the time starts from 0 and at time capital T, it completes one complete cycle. And RMS value is given by, so what is RMS? So root mean square, and here the order matters. So first we square the function, then we take the mean of that square of the function, and then take the square root in the end. So it is given by square root of 1 over t integral of f square from 0 to t. Let's do few examples. Find the mean and RMS values of the following waveform. So here we are given a waveform, and this waveform looks simple enough that we can find mean and RMS without integration. Why I'm saying so? Because here we see that we have some triangles, we have some rectangles, and we can easily find the area of these shapes. So a few things that we notice about this waveform. The first thing is that in this case, the time period is 8 seconds if time is in seconds. And since the average value is given by 1 over t integral of ft from 0 to t, so if we want to figure out the average value of this waveform, so that would be, so 1 over 8, so in place of t, we put 8. Ft dt, and ft is yt dt in this case. And as I said, this is a simple enough function that we really don't need to use integrals. So from 0 to 4, so if you want to figure out this area, so since it is above the x-axis, so it will be simply the area of triangle, right? And then we have another area which is below the x-axis, and we can subtract the area of, so this looks like a square because 4 to 8 we have this side 4, and also, so this is 4 and this is 4, so this is area of square. So area of triangle is half base into height. So base is 4 and also the height is 4. So we get um, 8. And similarly, if we look at the area of square, so area is 4 times 4, which is 16. So overall, we get area of triangle 8 minus area of square 16. So we get -1. So this is the average of our given waveform, which is -1. And as it is shown in the diagram, so this is our average. So in this case, it was very easy to find the area of the geometric shapes. But what if you don't have like such simple areas to calculate and you have to use the integrals in that case? And I can quickly show you the second method, that how can you find the mean of this waveform using the integration method. So first of all, we start by defining our function. So in this case, from the graph, we can see that, so between 0 to 2, we have a straight line which is increasing. So our function is of the form 2t between 0 to 2. And then we reach at 4. So 2 times 2 is 4. And then we have from 2 to 4, our function is a decreasing line with slope -2. So our function is -2t plus 8 between 2 to 4. And then between 4 to 8, our function is constant. So function is always a horizontal line, which is y equals to -4 between 4 to 8. So this completes our one period of our waveform. So that is our given function. And in order to find the average, we put the values in the formula. So 1 over t means 1 over 8, and 0 to t means 0 to 8 yt dt. And since this is our piecewise function, we can split this into three integrals. So we will split it from 0 to 2, and the function is defined as 2t dt plus integral 2 to 4, and the function there is -2t plus 8 dt. And then we have from 4 to 8, and the function is defined as -4 dt. And we know that integral of 2t would be t square over 2, so we are just left with t square from 0 to 2. And similarly, integral of -2t would be -t square. Integral of 8 is 8t, and then again the values limits are from 2 to 4. And lastly, we get plus -4t, limits are from 4 to 8. And when we put the limit, so you will notice that in the end you get -1, which is same as what we got before. So the average value of this function is -1, and it's represented by this pink dashed line here. So next we need to find the RMS value of this waveform. So in order to find the RMS value, it's always a good idea to make the graph of y square and then shade the area underneath it. So, or in other words, you can first find your function f square and then take the integration of that function. So if we try to write our function y square from our y, so we're just gonna simply square. So 2t square means 4t square when t is between 0 to 2. So -2t plus 8 square when t is between 2 to 4, and -4 square means 16 when t is between 4 to 8. Let's try to graph one cycle of this periodic waveform. So of y square. So on y-axis we will keep our y square. On x-axis we will put our time. So this is our starting point origin. So first between 0 to 2, 4t square. So it is a parabola and it is opening in the upward direction from 0 to 2, and the maximum value when t equals to 2, y square is 16. So we graph a parabola going up to 16. Next we have -2t plus 8 square. Again, this is a parabola, and this one you can think of as so -2t plus 8 square. So 2 common, so 2 square is 4. Inside you are left with this. So it's a parabola, and we can see that it's displaced along x-axis. So and then it's flipped, so it's gonna look like, so when t is 2, it's 16. When t is equal to 4, it's 0. So it's gonna look like this. And next from 4 to 8, y is always 16. So y is always 16. So it's gonna be our rectangle. So I'll just use a dashed line. Since RMS value is given by this formula, so we can put t is equal to 8 here. So integral from 0 to 8 of y square t dt. And now again, so this question you can do in two ways. Either you can use the geometric method and you can figure out the areas under these curves. So this curve can be divided into, the area can be divided into three parts. So we have part number 1, 2, and area number 3. So area number 1 and 2 are same by symmetry, and for third one we just have a rectangle. All right, so how to calculate area under a parabola, like area number 1 and number 2? So if you recall previously in one of the sections, I believe it was section 18, we had done that area under a parabola is 1/3 of base times height. So it's just like triangular area. So triangular area is 1/2 of base times height. So area under a parabola is given by 1/3 times base times height. So in this case, what I'm gonna do is I'm gonna here write my area number 1 plus area number 2 plus area number 3. So by symmetry of our diagram, so area number 1 and 2 are same. So area from 0 to 2 equals to 2 to 4, and that is given by, all right, so I'm gonna write 2 times. So 1/3 of base, so base in this case is 2 and the height is 16. So that is our area of parabola. And then plus area of number 3, which is area of rectangle, so that would be 16 times 4, because this is 4 and the height of the rectangle is 16. So when we solve this, overall we get, so we get that RMS value is approximately 3.266. So this is our geometric or simple method of how we find the RMS value of a function. But just keep in mind, like if you cannot find the areas easily, so these areas easily, so you need to use the actual integral. So you can just plug in the value of the function in the integral and solve for the integral. I hope that makes sense. So let's just do one more example in which exclusively we use our method of integration to find mean and RMS value of a waveform. In this example, we need to find the mean and RMS value of the given voltage waveform. So we are given the function of Vt. Two cycles are shown. T is in seconds, V is in volts. So first thing we notice that the period in this case is 4, because we are given the 2 cycles, and after this 4 seconds it starts repeating again the same pattern. And now we notice that we are given that Vt is equal to, from the graph, it's already given in the graph here, so 2 cube 2t cube minus 1. And we notice that again our function is over the period 4 seconds, it's piecewise. So first we need to figure out when does v becomes equals to 1, at what time v becomes equal to 1. So we need to figure out this x value and this x value. Let's put v equals to 1 volt here. So 1 is equal to 2t cube minus 1, and then from here we get 2t cube is equal to 2, and 2 times t cube minus 2 equals to 0. So 2 as a common factor out. So t cube minus 1 equal to 0. So from here t should be equals to 1 second. So it means when t equals to 1 second, voltage becomes 1 volt. So here we should have 1. And also we notice that by symmetry, the voltage stops being 1 when t equals to 3. So from 1 to 3, the voltage is 1. If you're wondering that how do I know it's symmetric, because it's given here that it's symmetric with other side. So using that reasoning, I say that it stops being 1 volt when t equals to 3 seconds. So now we're going to try to find the mean of the voltage function. So mean would be 1 over t. So that means 1 over 4 integral from 0 to 4 vt dt. So vt dt. So if we try to look at the area from 0 to 4, so we notice that this shaded area from 0 to 1 and the area between from 1 to 4, they are same by symmetry. So we can just find one of these pink areas and we can twice them. And then for the rectangular part, so this area is just 2 because from 1 to 3, so this length is 2 and the width of the rectangle is 1, so it means the area of this rectangle is 2 times 1, which is just 2. So now overall our average function becomes so twice the integral of, so the curve, but the part of the curve between 0 to 1, which is defined as 2t cubed minus 1 dt. So I'm doing it twice because that will accommodate also area from 3 to 4 plus area of rectangle, which is our yellow area, which is 2. So in case you're wondering, so this is my yellow area and this is my pink area. So twice of the pink area from 0 to 1. So that accommodates area from 0 to 1 and 1 to and 3 to 4. Thus, when we take the integral, we get so t4 minus 2t. So from 0 to 1 plus 2. And putting the lower and upper limits, so we get 0.25 volts. So that is the average of our voltage function. So if you want to draw it on the graph, so it would be 0.25. So that is mean value of our voltage function. Next, we want to find the RMS value or the effective value of this function. So that requires finding the area under squared function v square. Now we think about v square. So between 1 to 3, the region between 1 to 3. So if you just do square of 1 volt, that will be again 1 volt. So the region between t equals to 1 and t equals to 3 seconds. So we have v square is equal to 1 square volt. And also between 0 to 1 and 3 to 4, they're by symmetry. They should have the same area and we need to compute only one of them. So overall, what I'm coming at is, so our RMS value becomes 1 over 4, 0 to 4, v square t dt. So I would like to point, so if you're finding the RMS value, so you need to find, also take the square root of this mean of square. So this is our RMS value. So basically first we're going to figure out what is the mean of v square. So again using the same steps as previously we have done. So 1 over 4. So twice from 0 to 1, and now we're gonna do v square, so which means 2t cubed minus 1 square dt, and then for the other rectangular parts it's again 2 volt square between t equals to 1 equal to t equals to 3. So this was 2 units and then 1 units. So 2 times 1 is just 2 volt square. So now overall we get 1 over 4. So integral 0 to 1. So we're gonna expand this square and we get 2t6 minus 8t cubed plus 2 dt. So now this is easier to integrate. So we get, So 1/4 outside. So inside you're left with 8t7/7 minus 2t4 and plus 2t. And the limits are from 0 to 1 plus 2. And when we solve this, we get approximately, so upper limit minus lower limit, so we get approximately 0.786. Sorry, it's under the square root, so these many volts. And so square root of this is approximately 0.886 volts. So this is our RMS value of our voltage function, or the effective value of our voltage function. So basically, so you can use the integral formula to find the area under the curves that you cannot just do geometrically, and similarly for the RMS value you need to square the function.